Hi everyone, in this video we are going to take a look at chapter section 8.6. Please start working on your homework as soon as you finish watching this video. Okay, so in this chapter, we are going to cover how to measure the heat of reaction or enthalpy from using Hess's law. I'm going to talk about what is Hess's law in just a few minutes here. And for more detail of this chapter, please read the OER textbook chapter 8.6. Okay, so I'm going to use the knowledge that we learned in the previous video that we know that the amount of heat involved with the reaction is dependent on the amount of the substance. For example, if you are going to heat 1 cup of water versus a gallon of water, we know that heating a gallon of water would require more heat than a cup of water, right? So we're going to use that concept and idea and help us to understand what is Hess's law and how can we measure heat by using this method. Okay, so this amount that is effect on the heat of the reaction is part of the stoichiometry that you learned in the previous video as well. Okay, it's because as you see, right? So as you see that the what do you call it? There's heat involved, and if you have a certain mole of a certain substance, is going to involve with a certain amount of heat. If you double or triple, it's going to going to affect that amount also, right? By triple or double it. Right, so we're gonna use that. Okay, so we're gonna use the stoichiometry concept to help us understand this part better. The next one that we will also need to recall is that the change of enthalpy. Okay, so this one right here, or the heat of reaction, is a state function. Remember, as I mentioned in the previous video, that the state function is similar to like elevation, right? So in order for us to know what is the altitude, we need to have the reference point. So same thing here, right? So what we care about the change of the enthalpy is that at the reference, at some certain point that we use as a reference, and we are going to take a look at what is the final state, right? So we care about only the initial versus the final. We don't care about what are the route is take, right? So we just care about in this sense would be like elevation, right? So in this case, we're gonna look at only the difference in the final and initial state. We don't care about how it get there. Okay. All right. So let me take a look at example here so that way you understand this thing better. So let's say that we have reactant between carbon and oxygen. Carbon is going to combust in the presence of oxygen, okay, to form carbon dioxide. Okay, so carbon dioxide is the product. So let's say that there are two ways to achieve this, right? So one way is, carbon and oxygen react and generate carbon monoxide. This is going to be in the lack of oxygen, right? So it's going to produce carbon monoxide. So that's why, when you combust, natural gas at home, you need to have carbon monoxide detector because under incomplete combustion is going to generate carbon monoxide, right? So, or in the limit amount of oxygen is going to generate carbon monoxide. And this carbon monoxide, if you input more of the oxygen, if there are more oxygen available, this carbon monoxide will react more with the oxygen to actually convert to the complete combustion, which is carbon dioxide. Okay, so that's one way to do it, right? So it's two-step process. Another way is that if you have oxygen in excess, carbon can just combust with oxygen to generate carbon dioxide directly. Okay, so there are two ways. There's two routes to approach the same final answer or final product. So in this case, if you look at the heat that is involved with this, you will see that all of these are, I'm going to call enthalpy, right? So this is the enthalpy of reactant. This is the enthalpy of the final product. You will see that the difference between reactant and the product come out to be a negative value, which is negative 393.5. Okay. Now, if you're looking at between these two steps right here, okay, you're also going to see that it's come out to be a negative value as well. But if you add these two up together, it's actually equal to when you are doing the difference between the product and the reactant. So therefore, in this case, this is an example of the state function, right? We don't care how it get there. We care only the final and the initial, right? So we care only the final and initial. The difference of this is that what we care. We don't care about how we can achieve. So we are going to use this concept of that the overall enthalpy change for the reaction is going to come from the summation of each individual step that is related to this reaction, right? So we're going to use that Hess's law, which is what we know as Hess's law, to actually help us to manipulate other type of reaction. Okay, so let's take a look at this. So pretty much whenever that you are seeing the the given equations and also given the enthalpy change of the reaction as well. And it asking you to find out the enthalpy change of a certain reaction, know that that is the question that is going to be part of the Hess's law. Okay, so it's require you to manipulate the equation to get to the overall to the overall change of the enthalpy. Okay, so what do I mean by that? Okay, so first, before you get into anything else, let's take a look at one equation real quick. Okay, so if you have A plus 2B and it's converted to C and 3D, right? The heat involved would be 155 kilojoule. Okay, so the related equation, if it's giving you something like this, will you be able to figure it out? The answer is yes, you should be able to, right? So if you're looking at this, the given generic equation is going to be similar to what it's asking, which is 1A. The only thing that is different is you know that these two are different by 3 times, right? So that means if you multiply the given equation right here by 3, you are going to obtain this equation. Therefore, in this case, we already know from when we talk about stoichiometry, right? As you increase the amount, you are going to increase amount of heat as well, right? If you increase amount of substance, you are going to increase amount of heat as well. So in this case, the change of enthalpy involved with this equation right here would be 3 times. So in this case, it would be 465 kilojoule. Okay, so that's one way to do it. So another way is that if you're looking at this equation right here and you see that the equation is flipped, right? So in this case, because you flip the reaction, therefore, remember if the forward reaction is endothermic, the reverse process have to be exothermic, right? So if I, let me go back to this thing real quick. So as you see here, right, if you're going from reactant to product, if it's giving off energy, therefore the reverse process, if you're going from carbon dioxide to carbon and oxygen, it's going to absorb the energy with the same amount, right? So in this case, those two are just the reverse process. So the amount of energy involved would be the same, but the sign would be the opposite. If the forward is exothermic, the reverse process would be endothermic, right? So we discussed this before. So we're going to use that same concept here as well. Okay. All right. So in this case, because you flip the equation, therefore in this case, the amount involved with C, D go to A and B would be a negative value, which is the same 155 kilojoule. Okay. So what we can conclude is that if you double or triple amount, right, if you are multiply the equation by a certain coefficient, you are going to multiply the heat with that coefficient. If you flip the equation, then you have to change the sign of the delta H. Okay. So now what about this one right here? Well, clearly you flip it, right? So you flip equation and also you divide everything by half, or you multiply 1/2, right? So it's the same thing. You multiply by 1/2 or you divide by 2. It's the same thing to say it. Okay, so in this case, what you can do is you are going to flip it. So that means the sign would be a negative and you are going to half of 155. So you're going to get 77.5 kilojoule. Okay, so you get that idea. So this is like, it's kind of like straightforward, right? But on the exam, it's not going to be that straightforward because some reaction require multiple, what do you call it? Multiple individual step, right? So in order to get an overall equation. So in this case, an example that I'm going to give you is going to be this one right here, since it have involved with 3-step equation here. So this is an example of Hess's law problem. Hess's law is going to be asking for the overall heat of reaction that come from summation of the individual step, right? So that is the definition of Hess's law. So that means in this case, it's going to give you individual steps and it's asking you for the overall reaction. Okay, so in this case, we know that this is going to involve in Hess's law. Okay, so how can I manipulate that in order to get the overall reaction that I want, right? Because if you're looking at these two, they are nothing like each other. It's similar, but it's not the same, right? So in this case, you need to manipulate this equation first in order to get what we want. Okay, so how do we do that? Okay, what I highly recommend you to do is just use one reactant or one product at a time. Okay, so I'm going to focus on NO2, dinitrogen monoxide in this case. Okay, so let's find me where is the location of dinitrogen monoxide in any of this reaction right here. So where is it? Well, it's the third one, right? So it's the third one. As you see, the third one contains two N2O. Okay, this one contains just one, this one contains two. So that means somehow we need to make these to be the same coefficient as this one, right? Because this is what we want. This is what we want at the end. So therefore, in this case, you know that in order to make this coefficient to be the same as this, we need to divide this one, right, by 2. You agree with me? So in this case, we are going to divide by 2, or you can say that you multiply by 1/2, right, which is the same as divide by 2. Okay. So in this case, what you are going to do is that you are going to multiply 1/2 or divide by 2 throughout the whole equation. Okay, so if you divide this by 2, it's going to become 1. Divide this by 2, it's going to become 1. This, if you divide it by 2, it's going to become 1/2. Divide this by 2 as well, it's going to get negative 1, whatever that is half of that, right? So 163.2 divided by 2. Okay, so what you are going to get is going to look like this. Okay, and the delta H would be this number right here. So half of 163.2 is 81.6. Now we get the same, what we want now with the coefficient. You don't have to worry with anything else. You might ask me, hey, what about this? Nitrogen, oxygen, Ami, like I don't see any of that in here. Yeah, you don't see it because eventually it's going to cancel each other out. Okay, so you don't have to worry about that. So therefore, in this case, all you need to do is just worry about one step at a time. Okay, so the next thing I'm going to take a look at is I'm going to take a look at, I'm going to avoid NO. Okay, so what I'm going to tell you is I'm going to avoid NO. Why do I avoid NO? Well, because the nitrogen monoxide, if you're looking at this, nitrogen monoxide appear in two equations. One is right here, the other, this one right here. So which one you're going to manipulate first? I don't know, because if you manipulate one, it's going to affect the other one. So in this case, I would avoid this. I would avoid the species that appear in more than one equations. Okay, so that way you can just not confuse yourself. So in this case, I'm just going to go ahead, choose NO2, nitrogen dioxide, because there's only one place that nitrogen dioxide appear, which is the first equation. Okay, you probably notice that in this case, the desired equation that we are looking at, nitrogen dioxide is part of the reactant, but the given equation, this nitrogen dioxide is part of the product. Therefore, in this case, we need to, flip it, right? We have to flip it so that we are converting this NO2 to be reactant. We need to flip it. Okay, so we need to flip it. Not only that, not only we are going to flip it, we also need to divide by 2 as well, because the coefficient here is 2 times higher than what we want. So you need to divide everything by 2. Okay. If you flip the equation, this section right here is going to be part of the reactant, and all of this would be the product. Okay, so I'm going to flip it, and also I'm going to divide everything by 2. So therefore, this is going to become 1. This would be 1/2, right? This would be 1. So what you are going to get would be this equation right here. Okay, so you flip it and then you divide by 2 too, right? So that means that's what you're gonna get. And same thing, remember we said that if you flip equation, which is if you reverse the process, the sign of enthalpy change have to be flipped as well, because if it's exothermic, if you flip it, it's going to become endothermic, right? So in this case, the sign of the delta H would be a positive value. And because we divide by 2, the amount of heat would reduce by half as well. So that therefore, delta H that involved in this equation is going to come out to be positive and half of what is given here. Okay, again, do not worry about everything else in here, like oxygen and nitrogen. But what I would like to emphasize is looking at this, the last one that we have is nitrogen monoxide, which is this one right here. Okay, we know that the nitrogen monoxide, and we know that the only equation we have not used is this one right here, right? So we have 3 nitrogen monoxide here, and we have 2. But wait. The one that we just manipulate, this one right here also contains nitrogen monoxide, remember? So therefore, if you think about this, you have 3 nitrogen monoxide, you have 2 here, and you already have 1 here. Therefore, you don't need to do anything with this second one, this second equation, because if you think about it, right? So eventually, if you add these 2 together with this one, it's going to give you equal to 3. So therefore, I don't need to do anything to it. Okay, so in this case, I'm just going to leave as it is. If you leave as it is, delta H would be the same, identical. Okay, now remember Hess's law said that the overall step, this is overall right here, of the enthalpy change can come from the summation of the individual steps. So these are the individual steps. So that means you have to sum them, you have to add them together. How you add them is you are going to add reactant together, you're going to add product together. Okay, so this is what I mean, right? So for example, in this case, you're going to add N2O plus NO2 plus N2 plus O2. Okay, become N2 plus NO plus. Remember, half oxygen, add to half oxygen, you are going to get 1 oxygen plus 2 NO. Wait, these two are the same, so I can also add a 2, so it's going to become 3 NO. Right, so if I add these two together, it would be 3 NO. Okay, so it's going to be 3 NO. So I'm going to erase this one. Okay, so now any species that appear on both sides of the equation, you can cancel those. So in this case, you are going to cancel oxygen that appear on both sides. You're going to cancel nitrogen that appear on both sides. Eventually, you are going to get N2O plus NO2 become 3NO, which is exactly what we have here. Okay, so again, when you add them, you add all these reactant together, you add all these product together. Okay, and if you see anything that are appear on the same side, if you see something that appear on the same side, you add them together, right? So group them. If the same species appear on both sides of the equation, then you cancel them. Okay, so let me actually do that clearer. Okay, so in this case, I cancel off those. So this is the final equation that we have. Okay, so if you add each of those individual equations, your delta H, the overall delta H, you also have to add them all together as well. So this is going to be the amount of heat involved for this overall equation that we are looking at. Okay, all right, this reaction is endothermic. Okay, so because it's come out to be positive value. Okay, I'm going to give you a few minutes here to make sure you actually truly understand it by doing this problem yourself. Okay, so let's pause the video and complete this example right here, okay, in your lecture manual. After you finish, then you can resume the video again. Okay, so don't forget to do it yourself first. Okay. All right, let's take a look at your answer. Okay, so I'm going to again look at which one I can avoid or not. In this case, pretty much there's nothing that I have to avoid. Okay, so I can start with any of these. So I'm just gonna start with the first one, hydrogen gas. Okay, so we have 3 and we have 2. Given is 2, this one is 3. So what should I do? Okay, so I'm just gonna go ahead, multiply by 3/2, right? So that way, if you think about this, right, you have 2 here, and if you divide, if you multiply by 3/2, you cancel that 2, so you're gonna get 3 as a coefficient. So in this case, I'm gonna multiply by 3/2. Okay, and if I do that, okay, so I can look at ozone as well, O3. Okay, so O3 is on the opposite side, so therefore I have to flip this, and because this one is 2 times greater than the desired equation, so I have to divide this equation by 2. Okay, so after we know, all we need to do is just set that up, right? So I'm going to set that up, and don't forget to get the value of the delta H as well. Okay, so same thing for the second equation. Okay, so let's check your answer if you get the same. After that, then you can combine them. Okay, so 1/2 of oxygen can cancel out. So therefore, in this case, your overall equation come out to be exactly what we want. Note that when you are checking your answer, note that your overall equation have to come out to be exactly what you are looking for. If they are not the same, that means you manipulate the equation incorrectly. Okay, so after you get the same, then all you have to do is going to add all those delta H together to get the final delta H. Okay, so it's come out to be an exothermic reaction in this case. Okay, so again, pretty much look at each species and find that in each of those individual reaction, right, and see how you are going to manipulate them. Either you have to flip them or multiply by a certain value, right, and at the end you are going to add all of those equations together to get the desired equation. Okay, All right, so tip for Hess's law, as I already mentioned, don't deal with species that are present in more than one equation. Okay, so that's something that you have to tell yourself, okay, because if you start with the species that appear more than one equation, you are going to spend hours and hours trying to figure it out, and you will not be able to figure it out. Okay, so that's going to affect your exam time taking as well. Okay, so in this case, let's take a look at what I mean here. Okay, so we have this given equation right here, and we have this following equation. Okay, so what do I need to avoid? Okay, so according to this, clearly I need to avoid D, right? Because D appear in more than one equation. What else that I should avoid? Well, I should avoid C because appear more than in one equation. So that means you can start with A, you can start with A, you can start with B, it doesn't matter, or you can start with F, it doesn't matter. Okay, but avoid C and D. Okay, so so in this case, avoid those. Okay, and start with any of those. All right. So the problem that for Hess's law in your paper homework is going to be paper homework chapter 8.5 to 8.7, number 4 to 6. Okay, so number 4 to 6 will allow you to do this type of problem again. So you will get to practice more of how to manipulate all of these, right, in order to get to the overall equation or the desired equation. Okay, so it's similar to what we just went over. All right, so that's it. So the homework associated with this again is the paper homework. So start working on your homework as soon as possible. If you have any question, please do not hesitate to visit me during office hour.